All right. Now, we've been learning all about heat energy and how we can measure that heat energy by looking at the temperature change of products or reactants, right? And we know that delta H for this statement here is negative 2511 kilojoules. What does that mean? Delta H, negative 2,511 kilojoules.
I'm not sure I'm comfortable to say.
Well, it's telling us that the heat change, comparing the products to the heat of the reactants, and where is that heat stored, that energy stored?
Oh, the energy is stored in the bonds.
That's right. And so the heat transfer occurs because of the change of the bonds. The new bonds of the products have different energy than the bonds of the reactants, and so the delta H tells us the amount of heat change associated with the change in those bonds. So a negative tells us what?
That it's exothermic?
That's right. Negative means it's exothermic, and negative also means that it is this process is releasing energy, and that the products have lower energy than the reactants do. All right? So, we said this a while back, but we have to remind ourselves that this statement, the way it's written here, this chemical reaction, is intimately tied to this thermodynamic information, the delta H information here. So it's saying 2 moles of this chemical, acetylene, combining with 5 moles of oxygen, produces 4 moles of carbon dioxide and 2 moles of water, and releases 2,511 kilojoules of energy, of heat energy. Okay, so this 2,511 is specifically tied to this statement. Because of that, we can use it as a conversion factor and relate it stoichiometrically to the 2, the 5, the 4, and the 2. So the question is, how many kilojoules are released for every mole, 1 mole of this C2H2? Any ideas?
You just divide by 2?
Yeah, but what do you mean by that?
Well, 2 moles of C2H2 releases that much energy, so 1 mole is going to release half as much.
Very good, very good. So let's also write that down in a little unit analysis, right? To the right of our equal sign, what goes to the right of our equal sign?
Kilojoules.
That's right, kilojoules of energy. We want to know how much energy is released. That's what it's asking us. And what can we start with?
1 mole of C2H2?
Okay, I could start with the 1 mole of C2H2. However, if I do that, well, that's fine. Let's try that. 1 mole of C2H2. Okay, and then what am I going to do with that?
Well, you know, 2,511 kilojoules for every 2 moles.
Very good. 2,511 kilojoules for every 2 moles.
Do you have to include the negative sign?
You don't really, because the question is how much energy is released. If they wanted to know what the change in the heat energy was for 1 mole of the material, then yes, you would have to include the negative sign. But they're basically saying here how much energy is negative. So you don't have to include it. Okay, very good. Here's another scenario. Chemical reaction. How many kilojoules are required if 44 grams of carbon dioxide is to be consumed?
Well, I don't know, but I guess you could start with an equal sign.
Very good. You can start with an equal sign. What goes to the right of the equal sign?
Grams of carbon, kilojoules.
Kilojoules. Very good. Kilojoules of energy. And what do we want to start with?
We could try the 44 grams of carbon dioxide and convert that to moles, because we do know that 6 moles has a delta H of 2,816. This is positive. Does that mean that it's absorbing the energy?
That's right. That's right. This is how much heat energy is required for this process to occur. The positive sign tells you that 6 moles of this, 6 moles of that, 1 mole of this, and 6 moles of that, and requires, not releases, requires, that's the positive sign, 2,816 kilojoules. Okay? So if we say 44 grams, is that where you said to start?
I think I did.
Yeah, because we're going to go to moles, you said, right?
Yeah.
Okay, so moles of carbon dioxide. Do you know the grams per mole?
Oh, it's 44, it says right there.
Very good, 44 grams per mole. And let's see, are we done?
No, you're just in moles of carbon dioxide. You need to go to kilojoules.
How can I go from moles of carbon dioxide to kilojoules?
The equation says 2,816 for every 6 moles of carbon dioxide.
Very good. 2,816 for every 6 moles of carbon dioxide. So my moles of carbon dioxide are gone, my grams are gone, and I'm left in kilojoules of energy. Excellent job. All right. If 100 kilojoules are produced, what mass of carbon dioxide can be converted to our glucose? Now, C6H12O6, that is our glucose. So, what do you think?
Well, just use an equal sign. We'll get there.
Okay. What goes to the right of the equal sign?
Mass, grams of carbon dioxide.
Very good. Grams of carbon dioxide. Why don't you folks at home push pause right now and see if you can finish this up? All right. All right. Hopefully you took a chance to finish it up. What are we going to start with?
Well, we're given only 100 kilojoules of energy to work.
That's right. 100 kilojoules of energy. And so we need to go from kilojoules of energy to what?
The equation lets us go kilojoules to moles.
Very good. Moles of carbon dioxide. What was the numbers again?
6 moles of carbon dioxide and 2,816 kilojoules of energy.
Very good. So now I'm in moles of carbon dioxide. What do I want to do?
Just go to grams.
Very good. 44 grams per mole, right?
Yep.
Okay. Excellent job. So that should be 9.38 grams of carbon dioxide that I can get if I'm given 100 kilojoules of energy through this process. Okay. Meals ready to eat. Have you ever heard of MREs, meals ready to eat?
Yeah, I have.
Do you like them?
No, I don't.
You don't like them. Why not?
Because they taste gross.
You must have eaten a lot of them.
Yeah, I eat a lot. My dad was in the military and my mom was too. And they both brought them home whenever there was extras. And yeah, I didn't like them very much.
I love them. I love them. I hardly ever had them, right? But every time I did, wow, I thought they were wonderful. And they're a really essential part of the military, right? Because if you have a military and you can't feed it, then you don't have much freedom in your country. And if you have a military but you can feed it but not very good, then your freedom's not going to last very long, right? So meals ready to eat are nice because they have what's called a flameless heater. Do you remember how they work?
Yeah, you like to have a bag and you put your meal inside and then you add water to the outside of the meal and the bag inside the bag begins to heat and the meal heats.
That's right. Pretty good. That's good. So this is the chemical reaction that people are taking advantage of to produce their freedom, right? They are putting magnesium, or they're putting the water on top of magnesium metal. And you see how this single displacement reaction occurs, making magnesium ions and releasing hydrogen gas. So you never want to put a flame above your meals ready to eat.
Oh, wow, I didn't know that.
Yeah, but there's different ones now. They have different kinds of components, but they might release hydrogen gas in either cases, so you got to be ready. And it releases energy, 353 kilojoules of heat energy released. So if that's the heat that's occurring, and we want to warm a cup, let's just say 25 mils of hot cider, right? It's cold cider to start off with, but we want to heat it up to 85 degrees Celsius. And if we use the specific heat of water, because, you know, it's pretty much 100% water, right? And we assume that the density of the solution is the same, that's nice because that's essentially saying our 25 milliliters can be what?
I don't know. What do you mean?
Well, remember that to identify the amount of heat energy, right, that is required to heat an amount of a substance, in this case water, we need to know the specific heat of that material, We need to know how much mass we have of that material and how much you want to change the temperature of it. All those are factors in how much heat it's going to require to heat that system. Okay? And we know 25 milliliters, but we need to know mass.
Oh, but the density is 1 gram for every milliliter, so you can use 25 grams.
That's right. 25 grams, it can be my mass. All right, do you remember the specific heat of water?
Oh, it just says right there.
Oh, yeah. 4.184 joules for every gram that changes a degree Celsius. 25 grams, all right. And what's our change in temperature?
60, 25 to 85.
Very good. 60 degrees Celsius. Okay, so this will tell me how much heat energy I need to make this process occur, right? So, here we go. 25 times 4.184 times the 60. 6,276. 6,276 joules of energy necessary to heat our water. Now the question is, what quantity of magnesium do we need? How much magnesium do we need to do that?
So equal sign grams of magnesium.
Very good. Equal sign grams of magnesium. Starting with what?
6,000, what was it? 6,276 joules.
Okay, so we want 6,276 joules to heat it. And what do we know?
353 joules are released. No, 353 kilojoules.
Oh, good. Good point. Way to catch that. So that's 353,000 joules. Is it okay if I just write it like that so we don't have to convert it later?
That's okay.
Okay, that's how many joules for what? What are we going to relate that to?
To gram. Well, we can't go to gram. Let's just go to moles. Moles of magnesium.
Okay, how many moles of magnesium?
It just says 1 mole.
All right, so 1 mole of magnesium will release that much heat energy if it's reacted with water?
Yeah.
Okay, good. So, what's next?
Just convert moles to grams.
That's right. Moles of magnesium to grams of magnesium, and we'll be able to identify how many grams. How many grams per mole of magnesium?
It doesn't say. Do you have your periodic table?
Yeah, let me get my periodic table. All right, so what does it say?
24.43? 24.3?
Okay, so we're going from grams, 24.3 for every mole. All right, so 6,276 times our 24.3 divided by 353,000, right? Make sure you include all those zeros. And that should tell us how many grams of magnesium we need. So we need just 0.43 grams of magnesium to release that much heat energy. Okay, good work. Good work. Now you can go be free.